Good morning and welcome back to this course, to the third week of the course on fluid dynamics and turbo machines. In the last 2 weeks we have looked at introduction to fluid flow and the integral approach for analyzing fluid flows. In this week we will take up the another approach for analyzing fluid flows, that is the differential approach. So, the differential approach actually builds on the integral approach, that is why we have studied it before coming into the differential approach. We will use the concepts introduced in the last week during getting the differential equations using the differential analysis of fluid flows. So, let us go to the slide now. So, this is the first lecture of the third week. So, what we see here is we see how we look at how you can use the integral approach to get the conservation equations which were defined before. Now, if you see, we have looked at mass, momentum, angular momentum conservation during the last chapter. We will start with the mass conservation. Just to remind ourselves, the difference between integral and differential approach is, in the integral approach we write the conservation equation for a finite size control volume, like demonstrated in the tutorial problems in the last chapter, and in the differential approach we look at an infinitesimal control volume, very small control volume. The objective is to get differential equations for the entire flow field, not the overall quantities as such which is obtained from the integral approach like the force, thrust, etc., or torque. Here we want the full information on the velocity field. To get that, we have to solve appropriate differential equations for the entire field. The basic conservation equations are same, conservation principles are same. So, that is mass, momentum and angular momentum conservation, only it is applied to a very small control volume. So, let us start with the mass conservation equation. If you look at the mass conservation equation given by the integral approach, it has the first term which talks about the rate of change of mass in a particular control volume, and the second term is the rate of mass exiting the control volume, the total mass exiting the control volume, because there is flow through the control surfaces. In a control volume there can be mass exchange. So, there is flow through the, there is velocity at the control surfaces. To simplify our derivations in this chapter, we always consider 2D flow, a 2-dimensional flow. We can extend it easily if we understand the concepts, we can extend this easily to a 3-dimensional flow. So, we begin with a small infinitesimal control volume which is given as this A, B, C, D. The vertical direction is the y axis and the horizontal direction is the x axis. Now, the elemental size in the x direction, that is AD or BC, they are given as delta x, and the elemental size in the y direction, that is AB or DC, they are given as delta y. So, this is basically the size of the control volume. As we are dealing with a 2D flow, so the size of the control volume perpendicular to this slide is actually 1. So, if you want to obtain the volume of this control volume, it is just delta x multiplied by delta y multiplied by 1, that is delta x into delta y. So, let us keep that in mind and proceed with the application of this equation to this control volume. So, let us consider the location of the control volume with respect to the xy axis. So, let us say x comma y is the location of this control volume, and if we look at the velocity coming into the control volume through the control surface AB, it is u minus del u by del x into delta x by 2. How do we write this expression? So, to answer that question, first let us see, like we have defined this point x comma y, we have defined velocities at this point, that is the center of this control volume. The x directional velocity is u, and the y directional velocity is v. If we know the velocity, as velocity is a continuous function, so as we know the velocity at the point x comma y, we can find the velocity at the control surface from the same velocity and the velocity gradient information by using Taylor series expansion. So, how to do that? If we take this to this side, it is at a, because the size of the control volume in this direction is delta x, and the control surface is located at a distance delta x by 2 from the center of the control volume. So, we can write the expression for velocity as u minus del u by del x into delta x by 2. So, basically we do a Taylor series expansion and get this expression for velocity. Of course, the higher order terms can be neglected because this control volume size is very small. So, delta x square, delta x cube, etc., whatever appears in the expansion can be neglected. Now, this del u by del x is of course the velocity gradient at the same point x comma y. Now, this is the velocity coming into the control surface. The velocity going out can be obtained similarly, that is u plus del u by del x into delta x by 2. So, this is at minus delta x by 2 distance from the center, and this is at plus delta x by 2 from the center of this control volume. So, we can easily write these two expression. Writing the expression for any quantity defined at the center of a control volume at the control surfaces like this will be utilized throughout the derivations in this particular chapter. Now, as we have done in the case of u velocity, we can do the same in the case of v velocity. So, one thing you can notice here that we have made a little change in the symbols, because we have now defined the y component of velocity by symbol v. That is why we have defined the velocity vector in this equation as v1 bar. So, v1 bar has two components. The x component, it is for this particular case it is a 2 dimensional velocity field, and so the x component is u and the y component is v. And we also should keep in mind this v, small v appearing over here, represents the volume. So, small v represents the volume, which we have also indicated before. Now, this is the scenario of the mass or the velocities at the control surfaces of this control volume. This is what we used to do even in the case of a finite size control volume, like a plate moving by a jet which is coming onto it. So, after doing this, now let us see term by term how we can determine the value of this parameter. So, the first term is this, the unsteady term, which is given as del t of integral over the Cv rho dV. So, this can be written as, so rho in this particular control volume is not constant, but we can consider the rho at the center of this control volume, because this is a very small volume. We can consider the center density at the center, which is rho x comma y. In this derivation we are also considering density as a variable quantity, not a constant quantity. So, we can write this, we can replace density with rho at the point x comma y and assume that the density is not varying, at least for this expression it is not varying within the control volume. So, if you assume that, then you can take density out, rho out of this integral sign, and you can integrate over volume. So, if you integrate over volume, what you get is the total volume. Integrate dV over the entire volume, you get the total volume, which is del x into del y. So, this comes out to be, the first one comes out to be del rho by del t into del x into del y. So, this is quite easy to understand. Let us see the next part. The next part is this part. This part is actually net rate of mass exiting the control volume. That means the rate at which mass is going out of the control volume, for this case through this surface, that is surface AD and surface DC, minus the rate at which the mass is coming into the control volume through surface AB and surface BC. So, we do that systematically. we first find out rate of mass exiting in x direction. So, this is the x direction. To find out the rate of mass exiting the x direction, we can write it like this. So, now you can observe here that the density is a variable quantity. To find the second term, in this equation. So, rho as the similar to velocity, rho is a continuous function and it is defined as rho plus, by expanding it into a Taylor series we can define rho similarly as velocity. All the functions are continuous functions, so they can be their first derivatives are also continuous. So, assuming that, we can actually write it as rho plus del rho by del x into delta x by 2. So, this is the density at the exiting surface in x direction, that is the surface dc, multiplied by velocity u, that is what we have written here, u plus del u by del x into delta x by 2. So, this is rho density at the exiting surface, velocity at the exiting surface multiplied by the surface area. The surface area is this, just this length multiplied by 1. We have not written 1 here, but because it is 2 dimensional analysis, so we can just replace this by delta y. So, this is basically the mass which is exiting minus mass of fluid which is coming into the control volume in x direction. So, this can be again similar to this, written like this form. If we multiply these two quantities and simplify this expression, then what we will get is del rho u by del x into delta x into delta y. So, this is very simple, we can directly simplify this and get this expression. So, this is the rate of mass exiting in the x direction. Similarly, we can get the rate of mass exiting in y direction. So, we can write whatever mass is going out in the y direction from the surface AD, the velocity there is v plus del v by del y into delta y by 2, and the area is delta x now, because this is the area perpendicular to the v velocity. So, the area perpendicular to the v velocity in this control volume is basically delta x multiplied by 1. So, delta x, this is this expression is the mass, rate of mass entering the control volume in y direction. So, it comes in through here. So, like here we get a similar expression del rho v by del y delta x into delta y. So, we have everything now whatever is required to get the differential equation for mass conservation. So, this is the first part. So, net rate of mass exiting. Okay. So, before going into that, these two can be clubbed together to get the net rate of mass exiting the control volume, which can be written as a sum of this and this. So, del rho u by del x into the volume plus del rho v by del y into the volume. Now, we can club this part and this part, these two parts. This part forms the unsteady part of the equation, this part forms the part which includes the convective component. So, convective means the one which exchange through the control surfaces, the velocity or the mass exchange by velocity through the control surfaces. So, now we club these two parts together. If we club these two parts together, what we get is like this. So, this is our final expression. Of course, delta x by delta x multiplied by delta y is not 0. This is a infinitesimal but non-zero sized control volume. So, it can be taken out, that is not equal to 0. So, what is 0 is del rho by del t plus del rho u by del x plus del rho v by del y is equal to 0. So, this is basically our continuity equation, which is, or the mass conservation equation, which is applicable for a 2 dimensional compressible flow and unsteady flow. So, 2D unsteady because the unsteady term is retained here, 2 dimensional because only 2 dimensions are considered, and compressible because density has been considered as a variable quantity in this expression. We can reduce it to a steady and compressible flow situation. So, if you consider the flow as steady, of course, the first term drops out and you get this expression. So, this basically this is the continuity equation or mass conservation equation for a compressible steady compressible flow, del rho u by del x plus del rho v by del y is equal to 0. Now, we can also find out for a unsteady incompressible flow. We keep the flow unsteady, but we make it incompressible, but if you notice the only unsteady term appearing in the continuity equation, that means in this equation, is concerned with density, and by making the assumption that it is incompressible, this density is anyway constant. So, this drops out. So, this drops out even for a unsteady flow, and what we are left out with is this equation. As density is constant, it can be taken out. So, we can get this equation del u by del x plus del v by del y is equal to 0. This equation is same for a steady and a unsteady flow for an incompressible flow situation, because the only unsteadiness in the continuity equation pertains to the density. So, this is the equation which is valid for a 2-dimensional steady or unsteady incompressible flow. If we want a 3-dimensional flow, the simple difference will be, we will have another derivative, that is, let us say w is the velocity in the z direction. So, we will have del u by del x plus del v by del y plus del w by del z equal to 0. So, we have got the mass conservation equation from by using the integral analysis to a infinitesimal control volume. Let us now go to the momentum conservation equation. We take the same approach even for momentum conservation equation. What we do is, we start from the integral approach. In the integral approach, the velocity, the momentum conservation equation is written in this form. So, the left hand side comes from the Reynolds transport theorem, and the right hand side is basically the sum of all the forces acting on the control volume. This is a vector equation. So, again we consider this as a 2D flow, and if we consider it as a 2D flow, this has two components. So, unlike the continuity equation, the right hand side of the momentum equation, momentum conservation equation is non-zero. So, we will deal the left hand side and right hand side separately while arriving at the differential equation for momentum conservation equation. So, first in this slide we will take up the left hand side, which is the unsteady part of the momentum and the net momentum exiting the control volume. So, we take up this part, again we take 2D and we take incompressible flow. In the last case for mass conservation, we have considered compressible flow, but in this case we considered incompressible flow only because in the case of compressible flow, the density variation will make our expression very big. So, we want to keep that expression simpler, that is why we have assumed incompressible flow, but by considering density as a continuously varying function through the flow field, we can extend the same approach to the compressible flow as well. Okay, so, now let us look at this part. The control volume is the same. Again we have this two edges of the control volume defined as delta x and delta y. This is the point, and in this point we know the x comma y, this control volume is located at a point x comma y, u velocity, v velocity are x and y component of velocities. So, these were all defined in the last slide. So, we can quickly go over this. Now, let us see how to write the momentum conservation equation in x direction. Again we will only make the derivation for momentum conservation in x direction, and in y direction the same principle can be extended, same procedure can be extended. So, we will look at the momentum conservation equation in x direction. In the momentum conservation equation in x direction, we have the first term, that is the unsteady term. Let us take up that term first. In that term, again density is constant. So, density can go outside this derivative. So, we have taken out density, and within the control volume velocity for this unsteady term we can consider it as constant, and then we can again take this out, we can write this as del u by del t, integral of dv will be delta x into delta y. So, basically this is the expression which we get for the first term or unsteady term or rate of change of momentum within the control volume. The second term is the net rate of x momentum exiting the control volume. So, the first term was the rate of change of x momentum within the control volume, the second term is net rate of x momentum exiting the control volume. Now, this we have to do it very carefully. Let us see what is the we do it in a stepwise manner, so that we understand all the considerations here. Or so, first thing is rate of x momentum transported by u velocity. So, this is very important to consider, that x momentum, that is the momentum of the fluid in the x direction, is transported by u velocity, and it is also transported by the v velocity, by the y component of velocity. So, we deal with these two parts separately. First part is what is the rate of x momentum transported, or what is the rate of x momentum exiting the control volume which is transported by u velocity. So, this u velocity brings in the momentum of the fluid through this control surface and takes out the momentum in x direction momentum through this control volume through this control surface. So, we write it in that manner, x momentum multiplied by area in the control surface DC which is going out, subtracted to x momentum multiplied by area coming in through the control surface AB. So, through this surface. Now, we just need expression for this two. So, for expression for this two, we can write x momentum is basically rho velocity at the control surface multiplied by velocity at the control surface. So, this is the exiting surface, that means in the surface DC. So, in the surface DC, rho multiplied by u plus del u by del x into delta x by 2 whole square. So, basically that is the x momentum at the exiting surface multiplied by area, delta y is the area. Now, if we have taken it as a compressible flow, we have to replace this density with a variable quantity, that means rho plus del rho by del x into delta x by 2 for this control surface. But we want to keep the expression simple and basically demonstrate the procedure. So, this is basically the x momentum out of this control volume, which is transported by u velocity, and then this is what is coming in. So, now if we simplify this expression, we can write it as 2 rho u del u by del x into delta x multiplied by delta y. So, this can be simplified to this form. Basically, if you take rho into delta y out, then what you will be left out with is, you can see this looks like a plus b whole square minus a minus b whole square, which should be 4 into a v. So, 4 multiplied by u multiplied by del u by del x into delta x by 2. So, that comes out to be 2 into rho 2 into u into del u by del x into delta x, and rho into delta y was already there. So, we get this expression. So, we get the first component of the contribution of the first component, that means the x momentum transported by u velocity. Now, the second component talks about the rate of x momentum transported by v velocity. So, this is a very important thing to understand in this analysis, that although you might not have a variation in u velocity, but a variation in v velocity means I mean the spatial variation of u velocity is not there, but a variation of v velocity can bring about a rate of change of momentum or a rate of change of x momentum in the control volume. And why is that? That is because we have some x momentum in this control surfaces. So, in the control surface BC and AD, there is an x momentum, so which is given as this. So, u velocity here is if you know the u velocity here, like we did for this surfaces, we can do it in this surfaces also by using Taylor series expansion, and we can write the velocity as u minus del u by del y into delta y by 2. So, instead of del u by del x, it is del u by del y here, because we are talking about the variation in y direction, and u is continuous, whereas and its derivative with respect to x and y both are continuous. Now, we can write this, and we can write a similar expression on the surface AD. Now, if you see, even if you forget this part, this, let us say this two are same, the momentum coming through the x momentum coming in through AB is same as momentum going out through CD, that means these two velocities are same. Even under that condition, the v component of velocity can transport momentum, even a constant momentum can be transported, even if you consider this velocity, this u velocity is same as this velocity, but the variation of v velocity can result in a rate of change of x momentum in the control volume. So, that is very important to understand, and that is the quantity which we are trying to derive here, that rate of x momentum transported by v velocity. So, if you do that, again we can write in this form, this is the x momentum multiplied by area, which is exiting, means which is going out through the surface AD, subtracted to x momentum multiplied by area, which is coming in through the surface BC. Now, to write an expression for this x momentum multiplied by area, here we have to remember that this is the x momentum transported by v velocity. So, the expression for the momentum is rho multiplied by u velocity multiplied by the v component of velocity, because it is transported by the v component of velocity. Similarly, we can write multiplied by delta x because of the area, and then we can write the one which is coming into the control volume, rho multiplied by u component of velocity multiplied by the v component of velocity into area. So, this is basically the x momentum transported by, this is a x momentum, but it is transported by v velocity. This is the x momentum and transported by u velocity itself. So, that is the expression which we got in the first case. The second case is this. If we simplify this expression, what we get is like this. If we have to just simplify this entire expression by multiplying these two things, and then if we two expressions, algebraic expressions, and if we do that, we will get a final expression in this form. So, now by combining this two, by adding this two part, we get the net rate of x momentum exiting the control volume. What is that? It is basically this part, and here also if you see delta x into delta y, that is the volume appears in the equation. So, we get something like this. So, let us see this expression carefully. This part directly comes from the x moment rate of x momentum transported by u velocity. This has directly come from the rate of x momentum transported by v velocity. So, it has come from there. Delta x into delta y is a common factor in all these expressions. So, now we can simplify this further. What we can do is we can write it in this form. To explain how to write it in this form, we have actually broken down this first component, that is rho u, twice rho u del u by del x into delta x delta y into two parts. First part has been shown here, that is rho u del u by del x, and the second part is shown here, that is rho u, another rho u del u by del x, clubbed with this component, that means rho u del v by del y, plus this component, that is rho v del u by del y. Del x by del y appear in as a multiplier of these two expressions in both the factors. Now, if we observe carefully, we will see there is a reason for writing it in this form. If you take rho u out of this expression, what you get is del u by del x plus del v by del y, and that is essentially our continuity equation, and you can directly remove this from here, because we have taken this flow as a 2D and incompressible flow, and for a 2D incompressible flow, del u by del x plus del v by del y is 0. So, in this way, while deriving these equations, we have to make use of the continuity equation and simplify the expressions, so that we can finally get an expression which is meaningful. So, we get the net rate of x momentum exiting the control volume simply as rho u del u by del x plus rho v del u by del y, of course multiplied with the elemental volume. So, this is the final expression. Now, in this integral approach, if we go back, the first term was this, which was obtained as rho del u by del t into the volume, and the second term, that means the net rate of momentum x momentum exiting the control volume, has come out to be this. So, we club this two part. Let us club this two part. So, this is the first part and this is the second part. If we club this two part, we get this equation. This equation is basically the x momentum equation for a 2D incompressible flow, but of course the right hand side has not been simplified. So, we will do that, but before going into that, let us understand the meaning of this equation or the physical meaning of this equation. So, if you look at this equation, what you get is this is density and this is volume. If you multiply density with volume, you get mass. So, what this equation actually tells you is the total force or the sum of all the forces acting on the control volume is mass multiplied by a particular quantity, and that quantity has to be acceleration, as we all know. But this acceleration, so basically by doing all this, what we have got is an expression for acceleration. So, this part is actually the acceleration of the flow written in terms of the Eulerian velocity. So, we can write this because this is essentially, we know acceleration is the rate of change of velocity with time. So, in that sense we can write it as a derivative like this. So, this derivative is different from the partial derivative and it is called total derivative. So, this is capital D dt of u. So, this is basically the total acceleration of the fluid. What is the total acceleration of the fluid? We see it has two components. The first component is a unsteady component, and the second component has no time involved in it, which also explains that even in your Eulerian field or in your Eulerian description of velocity, which is the velocity is defined at a particular point and not for a particle, that particular velocity which is only defined at a particular point, even if it is not a function of time, you can have acceleration. How can you have acceleration? You can have acceleration because of this second component. So, the first component is the local acceleration, which consider the rate of change of velocity within the control volume with time, and the second part constitute of the convective component of velocity. In the convective component of velocity, what we have is basically the, along with the density, if we consider, it is the momentum exiting the control volume subtracted to the momentum which is coming into the control volume. Now, this part of velocity is very important to consider in the case of a description of a flow using a Eulerian field. This was demonstrated in our first chapter when we considered a flow field which is independent of time, but when we considered a fluid particle, the velocity of a fluid particle, it was changing with time. So, the fluid particle definitely experiences an acceleration, but the velocity field in terms of our Eulerian description is independent of time. If we now consider that velocity field which was independent of time and plug in the velocity values in this expression, we will see the local acceleration is 0 definitely because it is independent of time, but the convective acceleration is non-zero, and this contributes to the, or this explains the acceleration of a fluid particle as the fluid particle moves through this control volume. So, this is a very important thing to consider in our description of Eulerian field. So, finally, we can write our x momentum equation as rho du by dt multiplied by the volume with the forces is equal to the sum of the forces. Now, let us look at the second part, which is basically this part. We have already described the left hand side. let us look at the right hand side now. The right hand side is the sum of the forces. We will do that in the next slide. So, this is our complete expression. We have got the for the x component, we have got an expression for the left hand side, which is basically mass into the total acceleration. We have to find the forces now. So, we do a force balance in the x direction, because we are considering the x momentum equation in this derivation. Of course, 2D incompressible flow. Now, these are things which are known. If we look at, so while doing the force balance, we should look at all the forces acting in the x direction, which is the horizontal direction here. First, consider the shear forces which are acting on this particular fluid element. The shear forces, like we did for components of velocity and density, we can write the shear stress tau yx in this way. So, the shear stress on the top surface is different from the shear stress at the bottom surface. This difference in the shear stress will bring a net force in the x direction, which will be given by subtracting these two quantities. So, this is the first contribution. The difference in the shear stress is the first contribution considered in this presentation to the forces, to the net forces acting on the control volume. The second force which is considered here is the normal stresses, the forces due to the normal stresses. The stress acting on the surface CD and AB, they are not same, again they are different, like we had defined the other quantities, and the difference of the stresses will multiplied by the area will bring about a force acting in the x direction. So, this is the second consideration, and this is not all, because we have a pressure field. So, in the pressure field we have a pressure component acting on these two surfaces, like we did while drawing, while finding the forces in an integral approach. The sum of the forces, when we obtained, we consider the pressure field in the control surface. So, the pressure of course is acting inward into the control volume always, and then these are the forces. So, shear the forces coming from the shear stresses, the forces coming from the normal stresses, and the pressure forces, the forces coming from the variation or distribution of the pressure in the flow field. So, now we club them together, sum of forces, the first component is the shear stress component, of course multiplied by the area. What we observe here that is that in the case of shear stress, the area is delta x, whereas because it acts on the surface, on this surface, the other forces, that is the normal the forces due to the normal stresses acts on the delta y, the surface with area delta y, both these cases. So, we have multiplied this with delta y, and the third component is the pressure, which again acts on the surface delta y. So, these are the sum of all the forces acting on the control volume. Although this expression looks complicated, but it can be simplified, because if you look at it carefully, we see this two component cancels out, and these two components can be clubbed together, and if they are clubbed together for the shear stress, it can be written as del tau yx by del y multiplied by del x into del y, and similarly for the normal stresses and the pressure. So, if we do that, we get this expression, the del tau x by del y into del x del y, del sigma xx into del x del y, that is the volume, minus del p by del x into del x del y. So, this minus sign is because that the pressure is acting into the control volume on the control surface. So, now we have obtained the sum of forces. If we plug in this value here, what we get? We get the x momentum equation, which is the left hand side is rho du by dt and the right hand side is this. Of course, we have cancelled the volume, elemental volume, that is delta x into delta y from both sides. We are allowed to do that because delta x into delta y is non-zero quantity. We know that it is a non-zero quantity. If a non-zero quantity appears in the both sides of an equation, we can cancel it. If it is 0, we cannot do that. So, if it being a non-zero quantity, we cancel it and we get the final expression, that is the x momentum equation. So, this x momentum equation now is the almost close to the final form of the x momentum equation. We can write the total derivative in this form in the local acceleration and the convective acceleration and then write it. So, in this way we can also get the y momentum equation. In the y momentum equation, what we get is basically the shear stresses acting on the surfaces which are perpendicular to the x axis, and then we have the normal stresses which are acting on the y plane, that means y plane in both sides of the control volume, and we have the pressure forces. So, it is very similar. So, only acting in a perpendicular direction, but only with the difference that here we also have rho into g, that is the weight of the fluid inside this control volume. So, considering that, for y momentum equation what we get is a equation like this. So, if you see, it is very similar to this equation, only u is replaced with v, and the derivatives of pressure is with respect to y, which is understandable because we have considered the pressure variation in y direction, and similarly for shear stresses and normal stresses. Additionally, we have the weight of the fluid in the control volume in this expression. So, finally, this is our y momentum equation. So, now we have almost obtained the x and y momentum equation to, but this is not sufficient for us to solve or to get the information of the flow field, because we still do not know the expression for shear stress and the normal stress. So, this is the subject of our this will be the subject of our next lecture, where we will see how to express the shear stresses and the normal stresses in terms of the velocity component, so that we can get a partial differential equation for only in terms of velocities, and also pressure is coming in here, and we can get the flow field. So, in this brings us to the end of the first lecture of the third week, where we deal with the differential analysis. What we did here is we started with the integral approach and applied to a infinitesimal control volume. Then we looked at the left hand side of the Reynolds the left hand side of the conservation equation from the integral approach, that is the Reynolds transport theorem. Then we from there, by considering that, we get the expression for the total acceleration, which constitute of the local and the convective acceleration, and then by considering the sum of forces we finally got the x momentum equation, and similarly showed how we can get the y momentum equation. In the next lecture we will take up the how to write the shear stresses in terms of the velocity field. Thank you.